Hello, and welcome to this talk on scaling and optimizing the training of predictive models. My name is Nicholas Mitchell, and I'm a machine learning engineer at Argo AI, working on the perception stack for autonomous vehicles. I'm also a researcher at the University of Augsburg in Germany. This presentation will cover some work that I completed earlier this year. There are a lot of moving parts, so we'll stay quite high level and a lot of ground to cover, so let's jump straight into it. Let us begin by having a brief look at the challenges of modern machine learning projects, especially those in industry. So it's common knowledge that data sets keep growing and growing as we get better sensors and more sensors. And this means compute and storage need to grow with any solution that we might come up with. There are complexities around the model, and the size of the complexity keeps growing, especially when we think that modern machine learning normally means deep learning. And these are sort of being improved year on year at drastic rates. So time to optimize these models generally also increases as we have bigger models and more intricate models. There's a cost trade-off to be had when we keep in mind that we're in industry, and when thinking about the design decisions for scale, there's a need for efficiency and for flexibility. We need things that are going to work for quite a long time. And we need this flexibility to sort of allow us to be faster if we need to be faster, or to maybe save money if we need to be a bit more frugal with our training resources. And there are often production constraints. So maybe we need a model for a specific task and we have a specific budget in terms of time or in terms of compute or in terms of money. So we need to keep that in mind. So given these challenges, what do I talk about in this presentation and who might benefit? So I assume you have a working model. So yay, my model is training. I assume you have the problems, however, that you have large data sets that may continue growing. And so you might want to think about how to distribute this training. What are some tools for that? You might want to also keep fine-tuning a model either on new data coming in, or you want to keep tweaking the model. So you want to know how to tinker with hyperparameters of a model to squeeze the last drop of performance out of it. And we also want to do it efficiently, and so we need to think of a way that allows us to change our approach over time without reinventing the whole training pipeline. So we're talking about machine learning, and the star of the show here in this story is, of course, the predictive model itself. However, for the sake of this talk, let's keep it generic, and when we think about the model, let's think about something that takes an input and returns an output, so really just any predictive model. The specific goal that you have when you're approaching one of these projects might mean changing some parts of the pipeline that I'll talk about in ways to optimize the model. So again, the model itself is not the focus of this talk, and we'll maybe generalize to some common models later on. So let's look at the supporting characters of the story. There are three of them. So when we do modern machine learning, the compute is a big aspect of it. This is the physical hardware that we're going to talk about, or rather how to get access to it. The second part is then the orchestrator. So once we start thinking about a lot of data and distributed setting, we need someone to hook everything together for us. So that's the orchestrator, and then we need the brains. This is going to be the optimizer, which is going to be approaching the question of how to deal with all of these hyperparameters. So for each of these, here are some of the tools that I'm going to refer to, the ones that I've worked with, and I'll explain some of them in I'll explain compute and orchestrator at a sort of high level. I assume a lot of software engineers are fairly familiar with these tools, or one of a variant of these tools. I'll spend a little bit more time explaining the brains, this AutoML, and how the optimization could work for a machine learning model in a distributed setting. So the compute, this is perhaps the easiest decision. It might already be decided for you, but based on your company or based on your location. So you might already be using one of the three in the top right here. One thing, if you are at the very beginning and you still have the chance to think about it, is the on-premise versus cloud discussion. So if you are, for example, a small company, it might be worthwhile actually investing in a couple of good computers to have in your office as opposed to using the cloud. There's a reference at the end of this slide that will maybe help you decide if you're still in the early stages. So beyond picking a provider, probably one of those in the top right, it's also important to then look at the type of instances that they offer for their cloud computing, which hardware is available, and what you need for your specific model. If you need a lot of CPU power to quickly churn through some lightweight models, or whether you need big heavy GPUs for training one big monolithic neural network, for example. The orchestrators, these two in the top right, Docker and Kubernetes, they together offer quite a lot. So first, looking at Docker, we can think of Docker as a way of managing our dependencies. So everything is configured in a file, and that can be checked into a Git repository, and it can be shared, so we can get some kind of reproducibility and also easy collaboration, because we just send a Docker file to somebody and they can exactly repeat our experiment given the source code. It also allows a fine-grained interface to the hardware, so through the Docker API it's possible to also constrain for example, the number of CPU cores or the number of GPUs that are visible to a task. That's quite key when you come to a distributed setting, and we might want to, for example, use several of the GPUs on one physical machine, and we can make sure that that each instance of a model that's training only sees what it needs. So Kubernetes, upon which Docker really sits, it's a way to efficiently scale and manage different services. So in our case, one service might be training our model one time. So there's a way to bring those all together and allow automatic scaling, so more or less compute can be configured automatically through Kubernetes. It offers some fault tolerance, so if something goes wrong, it can restart it. And it also allows us some way to introduce networking and allow our jobs to communicate with each other, and maybe only certain jobs need to speak to other certain services in your training pipeline. So Kubernetes can manage all of that for you. The third character here, then the brains. So we can treat this as a black box. And if we do so, then it would be this kind of sentence here. You would say, I tried this configuration for my model, and this was what the model did. That was the result. Please tell me, what should I do next? The AutoML team in Freiburg, Hanover, the two universities in Germany, they have a range of optimization tools, and the one I'm going to be talking about is based on these components, Hyperband and Bayesian optimization. So Hyperband, in one sentence, it's a way to efficiently try out a lot of configurations. It's like doing a random parameter search, but very systematically and less randomly, breaking it down. We'll go into that. And the Bayesian optimization here, the definition straight from Wikipedia. So usually employed to optimize expensive to evaluate functions. And what is more expensive than a modern ResNet 101 model? So these come together, and the implementation is the BOHB Hyperbandster. This is essentially the combination of Hyperband and Bayesian optimization. So they're important concepts. So let's look at the first concept, which is Hyperband, and how that works, how we might use it. So let's imagine we begin here with a graph, and this is looking at our model and when we're training. And on the y-axis here, we have an error metric, so this can be the loss of the model, for example. And we can see on this axis that lower is then better, of course. On the x-axis, we have time, and the time here is how long the model is training for. So this can be the wall time, for example, of a model. And that's generally equivalent to money, because we're paying for our compute by time usually. So if we were to train naively, what we would generally do is a parameter grid search, for example, or random search. And what this might end up with is we start training a model and we see over time we have a loss curve which comes down and we end up here, so not quite in our target area. And so we try a lot of these random search fashion, and we have some like this. Maybe one converges quickly and ends up doing terribly. Maybe some just are terrible in the beginning, and perhaps there's a lot which just are in this sort of gray zone of where models fall bad convergence or would need a lot of time, a lot more data. So in the end, you can see we found a fairly good solution here, not quite in our target area, but not bad. However, if we think about the total cost of doing this, it's kind of equivalent to the length of all of these lines. So every line there is time spent training, time on compute, and this is a lot of black ink here on the paper. So let's start the graph again, and this time let's explain what Hyperband does. So Hyperband first looks at your time, and you would define a budget and how much time you're going to allow. And Hyperband would then proceed to break down the time, let's say, into 3 rounds. So we're going to have round 1, round 2, and round 3. This is all configurable. So we would begin by training some models as was done before, maybe by a random selection or a parameter grid, and we have some loss curves as before, terrible one that converged very quickly, and one that was going quite well here, one's quite slowly, and maybe we get again all of this noise here. But what Hyperband would then do is look at these and take the most promising only to continue into round 2. So there's a culling of the weaker models. So we would say this one is good, this one is good. Maybe let's take the best 3, the best lower proportion, and then let's just take a couple of random ones here and here selected from this mass just because they might turn out well. So then with these 5 we continue. This one doesn't do so well. This one continues. This one continues, maybe. This one goes down, becomes the best, and this one just pans out. We do the same again here. We take maybe this one and this one, and then maybe randomly select one of these 2. And in the final step, we continue training down, and we end up with here one which is in our target area. I mean, the target area is generic, but we've reached a quite good performance here. And if we look back and think about the line lengths here, if we were to add up the length of all these lines, it's actually way less than in the previous case. So we've reached here a better solution in this fictive example. But we've spent a lot less compute, and that's the main idea behind Hyperband, so quicker convergence. So let's go back and just put that together with Bayesian optimization. So this is the graph straight from the paper about this BOHB, and we can see here that from the orange lines, Hyperband on its own has a very quick convergence, a 20x speed up at the beginning compared to a random search. And at the end, it doesn't perform so well, however. The red line, on the other hand, the Bayesian optimization, is very slow to converge at the beginning, but reaches a really nice performance towards the end after training for a long time. The green line here is simply the combination of those two. So we've got the BOHB, getting the quick convergence of Hyperband, and then Bayesian optimization coming in strong at the end to squeeze out the last performance points. So we have a well-trained model here, and equivalently to a random search, we've got a 55 times speed up. So that's the optimizer, and we'll see now how that fits into the broader scheme here. So the basic training loop we see here for training a machine learning model, for example, In the middle, we start with the model. So we've defined a model which needs an input and gives an output. And there's a configuration which normally says how the model should be run, should be executed. It can hold things like learning rates for neural networks, or it can hold number of trees in random forests. And the other thing that the model needs access to is, of course, the data. So those two flow into the model trains, and there is some kind of performance metric, how well is the model doing, and this loop continues. So the model is then maybe tweaked, or it gets feedback, and it continues training until we're happy. And at the end, we have this gray line, and at that point, that's where we would probably take our model and go into production and deploy it and get some real-world feedback. Then this basic loop would continue, making any tweaks you see fit. So bringing in the tools that I spoke about earlier, we can augment this basic loop to the better loop, I've called it. Here, the only additions are those towards the top. So we have an optimizer in the picture now, and we can see from all of this is encompassed with Docker and Kubernetes, and then running, in this example, on AWS. So in this case, the model, again, needs to receive a configuration and have access to the data, but it's the optimizer that's controlling the configuration. So the optimizer here, the BOHB that I spoke about, this sees a configuration defined, a configuration space, and it will, in the first round, select some configurations, a couple of those, and it wants the model to train on those configurations. And then the performance metrics will be fed back to the optimizer, which can then say, okay, based on these performance metrics I'm seeing, which configurations should I choose next to optimize? Which ones should I definitely avoid? So it's a smarter way to search the configuration space. So taking now Docker, Kubernetes, and scalability of compute into account, what we notice is the optimizer says, okay, I want to try these N configurations, maybe 5, maybe 20, and then I wait for the results of all of those to come back. So that's a very parallelizable problem, really. So what we can do here very easily with Kubernetes is just say, okay, I'm going to have 5 models. So this could be 5 instances on AWS, each of which gets a configuration. It gets the Docker image to run a model with that configuration, and 5 results are then sent out and come back to the optimizer, and this can continue. So now we've just basically cut the time required by 5, and the optimizer can optimize more quickly because it's getting feedback more quickly. So that's the general overview of how these things fit together, and it's also a good benefit of this abstraction here. We have a Docker which can run a model, and the model is something that is generic, as discussed at the beginning. So something that takes some configuration and returns some performance metric to be optimized. And this model can really be anything. So this setup here on the slide with the scalability and this optimizer can basically optimize any model that can return an error metric. So this doesn't have to be just a neural network. It doesn't even have to be just a machine learning problem. It could be anything. It could be the analytical solvers used for motion planning, for example, in robotics. So one example with some real numbers, just to give a feel for it. So I've trained one large model, for example, with 80 GPUs, which was 10 8 GPU instances. I said to the optimizer that it can have 3 full training cycles. So for example, if a model needed 100 epochs to train, 100 times through the data, I said to the optimizer, you're going to have 300 epochs budget and use them as you see fit. I had a 10-dimensional hyperparameter grid, so that means 10 different parameters were being searched at the same time. And this ran for a total of 3 days in this case with that compute. Another thing that you could think about here, reusing the schematic and the slide before, is if we were to just provide one configuration, so the optimizer really had nothing to do, we would still really be able to take advantage of the scalability. So we could automatically scale up our training to just use 8 GPUs or 100 GPUs, depending on if we have priority to train our model quickly or not. So it's another flexibility that is offered to the machine learning engineer in this case. So that's all for the story. And one last point I'd like to make is just that all of this was done with open source software, which is amazing in my opinion. So the main ones here are I use Python for all of the scripting, and then Docker, Kubernetes, AutoML, all based on Ubuntu, and I used PyCharm. So all of that was free. And a couple of honorable mentions. I used TensorFlow here for some of the neural network components, and another tool to help multi-GPU training of models is Horovod. I recommend people look at that if they need multi-GPU training. And for logging of all of these experiments, there's the MLflow library, which could then log the progress, for example, of each of the configurations that were being trained. So I didn't need to wait to the end to see results. I could see that in real time while they were all training. I've got some references here, which will be in the slide deck that you can get with this talk. And with that, I would like to finish and be excited to hear any questions that you have.